Hi guys, welcome to 2.2 Toolbox Functions and Transformations. Just a friendly reminder that this Chapter 2 material is a review of your college algebra, so I will be going through it quickly. If you have any questions, be sure to bring them to our Zoom meetings. You are expected to be able to recognize and identify our toolbox functions. So these are just basic functions. You can see pages 120, I think 120 and 121 in your textbook for more details. But the first one is the identity function, f of x equals x, or just simply y equals x. And y equals x is the diagonal line passing through the origin in the first and third quadrant. You can make a table of values and see that the input produces the same output. Absolute value function, y equals the absolute value of x, is just our v goes to the origin in the first and second quadrant. Y equals x squared, or basic quadratic functions, any polynomial with the highest degree of 2. And then we have our square root function, right? That the domain is just non-negative numbers. The range is also non-negative numbers. So this is just a handful of functions that you should be able to look at the graph and recognize that it could be this function, or look at the function and be able to picture the graph in your head. Also the cube function, x cubed, looks like this. This is an example of an odd function. What's happening in the first quadrant is a double reflection of what's happening in the third quadrant. Likewise, same with the cube root function, which is just a flip of the cube function. What we talk about in this section is just a quick review of our transformations. We have horizontal shifts, moving it right and left, vertical shifts up and down, horizontal stretching, making it taller, and horizontal compressing, smushing it. So when do these things happen? Well, let's take a quick look at the graph of the absolute value of x and compare it to the graph of y equals absolute value of x minus 3. We added a minus 3 inside the absolute values. How does that differ if we subtract 3 from the outside, or we put a 3 out front, or perhaps the reciprocal 1/3 out front? So here's our basic absolute value function. Y equals the absolute value of x. It looks like this. How does y equal the absolute value of x minus 3 look? Well, you may already know what to expect here. If you're not sure, then we can start with the table of values and see what happens. If x is 0, we get 0 minus 3, negative 3. The absolute value of negative 3 is 3. So now we're at this point at the origin instead of 0, 0. If we're at 1, we get the absolute value of negative 2, which is 2. So at 1, we're at 2, 1, 2, 3, 4, so that would be right here, right? At 2, absolute value of negative 1, which is 1, right? At 3, we're going to have the absolute value of 0, which is 0. Right, at 4, we can have the absolute value of 1, which is 1. At 5, we're going to have the absolute value of 2, which is 2, and we can start seeing that the general shape doesn't change. Here we still have the shape, right? But it moved the graph of absolute value of x to the right 3. So notice we're taking the absolute value of x as well as the subtracting 3 is inside the absolute value with the x. So what we're doing to x, we're also doing, this 3 goes along with the x. So that results in a horizontal shift along the x-axis. So if what we're doing to the x, we're also doing to the 3, then the shift is in the horizontal direction. Minus 3 produces a shift to the right, plus 3 would produce a shift of 3 units to the left. If the minus 3 is outside of the parentheses, well, things happen a little differently. We'll make a table of values over here, right? If I start with 0, well, we take the absolute value of just 0. So we're not taking the absolute value of the negative 3. That's an afterthought. So the absolute value of 0 is 0 minus 3 would be negative 3. So at 0, we're now at negative 3. At 1, we're going to have the absolute value of 1 minus 3, which is negative 2. So at 1, we're going to be down here at negative 2. At 2, we'll be at negative 1. Right here. Right, and I can kind of see what's happening here. At 3, we'll be at 0. right? But if I do -1 also, so I do positive -1, if I do -1, the absolute value of -1 is also 1 minus 3. We're going to be at -2. If I do positive or -2, the absolute value is the same. My output's going to be -1. So I see right here, this is an even function. Switching the sign of the input keeps the same output. Right, so we have our absolute value shape is maintained, although it moved down 3 units. Right, so I call this guy a dangler. If it's outside the operation, we're not taking the absolute value of it along with the x, then it's going to result in a vertical shift. A shift along the y-axis, because it's we're not doing to the 3 what we're doing to the x. So we're going to shift it down 3 units. If it was +3, we would shift it up 3 units. And sometimes it just takes plotting a couple points to see what's going on here. All right, what happens if we throw a 3 out front? Well, let's make a table of values. We expect this to still have that V shape. Right, if x is 0, 3 times the absolute value of 0 is still 0. If I put in 1, we're only taking the absolute value of the 1, so it's 3 times 1, which is 3. So at 1, we are already way up here at 3. It's definitely a little bit different of a shape. At 2, the absolute value of 2 is 2, times 3 is 6. So at 2, I'm already way up here. Right, if I plug in 3, I'm going to be at 9 outside of my viewing rectangle. But I can see the pattern, and this is what's happening to the right of 0. Well, if I put in -1, well, again, this is an even function. It's going to produce the same output, 3. So at 1, or at -1, we're here at 3. At -2, we're back up at 6. So it looks like this. So notice this is a lot thinner and taller than the original absolute value function. So we call this a vertical stretch. Of 3 units. Right. So notice 3 is greater than 1, and that's important. And you'll see why in the next it's a stretch, because 3 is greater than 1. So I'm going to go down here to this last graph for a minute, and then we'll revisit the one in the middle. What if I chose to do 1/3 instead of 3? Well, we have x, we have y. If x is 0, we're still at 0. But if x is positive or -1, well, the absolute value of positive or -1 is 1 times 1/3 is 1/3. So if we go over 1, we're going to be right up here at 1/3. So that's 1/3 about right here and here. Right there. If I do positive, I'm going to do positive or -3 for simplicity. The absolute value of positive or -3 is 3 times 1/3 is going to be 1. So we're going to have to go all the way out to 3 before we get up 1 unit. Right, so I can start seeing this V shape. I'm going to do 6, again for simplicity, because I like taking 1/3 of 6. 6 is a multiple of 3. The absolute, whoops, I forgot to put that there. The absolute value of 6, positive or -6, is 6 times 1/3 would be 2. So we're going to have to go all the way out to 6 to get up to 2, or out to -6. So we still have this V shape, although it's not super mathematical, but I say we smushed it or compressed it. So this is a vertical compression. Right, so it's compressed or smushed, and it's smushed since 1/3 is less than 1. I should put is also greater than 0, right? So what happens when our numbers are negative? Well, if we ignore the negative sign, the graph of y equals -3 times the absolute value of x is going to look like this guy, although negatives in front, if your coefficient is negative, it's just going to flip it over the x-axis. So if we were to plot points, it would look like that. So let's just plot a few points. So we expect it to be 3 times as tall as the absolute value, but flipped over the x-axis. So at 0, we're at 0, positive or -1, we're going to be at -3, positive or -2, we're going to be at -6. So here we're going to be, oops, I'm going to be way off. So positive and negative 1, I'm already way down here at negative 3. 0, negative 3. 2, I'm already way off my graph. I didn't give myself enough room, right? So here, this is going to be a stretch of 3. So stretch 3 units, and the negative sign is going to flip it about the x-axis. Right? And this doesn't just work for any, it doesn't just work for the absolute value, it works for any function. If we replace x with x plus or minus a number, we're going to shift it in the x direction. If we replace y with y plus or minus a number, because technically we can bring that over to that side, we're going to shift it in the vertical direction. If we add a coefficient out front, it's either going to stretch it or compress it. If the coefficient is greater than 1, it's going to stretch it. If the coefficient is between 0 and 1, it will compress it. A negative will do either one of these things and then just flip it over the x-axis. So if I gave you this graph and I just said describe in words what's happening here, right? You could tell me that this is going to be a shift of 1 unit in the x direction, but because it's plus 1, it's going to be left. Shift of 1 unit left, right here. This is minus 1.5, so this is going to give us a shift of 1.5 down. If it's plus inside the operation, it's to the left. If it's minus inside the operation, it's to the right. On the outside, if it's minus, it's down. If it's plus, it's up, right? We're going to stretch it by a factor of 2. And then the negative sign will be a flip about the x-axis. So that's what I'm going to expect. I'm going to expect my absolute value function, which looks like this. Doing it lightly with pencil. All right. We're going to move it this way. We're going to move it this way. We're going to flip it, and we're going to stretch it. So let's just plot a few points. Let's see where that gets us. All right. I'm going to do, I'll start with 0. Right, so 0 is 1, negative 2. So absolute value of 1 is 1 times negative 2. Negative 2 minus 1.5 is negative 3.5, which would be right here. Right, at negative 3.5. At 1 will be the absolute value of 2. Negative 4 minus 1 would be negative 5.5. So I already know I'm shooting down pretty quickly. If I do 2, so let me see, I said 2, 4, negative 5.5. If I do 2, we're going to have 3 times this, negative 6, negative 7.5. So at 2, we're way down here. So I can see that as x gets bigger, y becomes more and more negative. All right, let's see what happens at negative 1. Well, negative 1 is going to give me 0 in the absolute value. Negative 2 times 0 is 0, minus 1.5, negative 1.5. So 1.5 would be about right there. All right, negative 2. I'm going to start looking for that symmetry. We know that this is going to be shaped like a V, but it's going to be upside down and moved a little. At negative 2, negative 2 plus 1 is negative 1. Absolute value of negative 1 is 1. Negative 2 times 1, negative 2. So here, so now I'm back to the negative 3.5. So at negative 2, I'm at 3.5. So it's going to go up. And it's going to come down. And without too much ado, I'm assuming at negative 3, we're going to be the same value we are at 1. I'm assuming it's going to be negative 5.5. Same value it was at 1. So let's put in negative 3. Negative 3 plus 1 is negative 2. Absolute value of negative 2 is positive 2 times negative 2, negative 4, minus 1, negative 5.5. So we see the pattern, and this would be the final result. All right, again, this is just a quick reminder on how these work. Please make sure you're looking at both the homework and the text and the Alex homework, and come by with questions, comments, concerns. All right, thanks guys. See ya.